Welcome to lecture 14.2 of our group theory course. This is the final lecture of chapter 14 and actually the final lecture of our course. The remaining chapters are going to be covered by seminars from the students, as we have discussed. So let me continue from where we stopped last time, which was the discussion of crystal field splitting when you consider spin-orbit coupling and double groups. So this is what we have discussed so far, the splitting of a given impurity level of d character, a d orbital impurity level, in two different possibilities. In the first case, the crystal field perturbation is stronger than the spin orbit perturbation. Then it makes more sense first to see the splitting of the d level like we did before, first considering the splitting due to the crystal field, and after that we introduce the spin orbit perturbation and see how the levels split further. And we also discussed the second case scenario in which the spin orbit is stronger than the crystal field. In this first case, this is more a more convenient description for transition metals of the 3D group with open 3D shells. And in the second case, this is a more convenient description for the D shell of 4D and 5D metals. And so in this case, it was more convenient to first do the spin orbit coupling on the free ion, and we see the splittings caused by the spin orbit coupling, and after that we add the crystal field perturbation. But you see that in both cases the final result is the same. It's just a matter of interpretation of the results, and from a more physical point of view, the two descriptions make more sense in each of the two different cases, but the final result must be the same. So what we are going to do now is to consider rare earth systems with open F shells, F levels, and there are two cases to consider. So in this case, clearly the spin orbit is stronger than the crystal field, so it makes more sense to first to do the spin orbit splitting, and after that we do the crystal field splitting. But there are two different cases corresponding to the two possibilities. In one case, the total angular momentum J is integer, and in the other possible case, the total angular momentum J is half integer. Okay, so the first case is, for instance, the holmium 3+ ion. Holmium 3+ has an electronic configuration 4f10. It has 10 f electrons from the 14 possible, and 5s2, 5p6, and if we use Hund's rule, we can find the ground state configuration of the holmium 3+ ion corresponding to the quantum numbers s equal to 2, l equals to 6, and j equals to 8. So, and in the spectroscopic notation, this means that we have discussed this notation in the previous lecture. This means that this ion is corresponds to this term. So we are dealing with the j equals to 8 system, so it's an integer. this is the case in which the total angular momentum quantum number J is an integer. So this will give rise to ordinary representations rather to double group representations. So in some sense, it's not very much different from the case of an integer orbital angular momentum quantum number that we discussed back in chapter, I think, 5 or 6. Okay, so the way to proceed is then to apply this formula for the characters of a given symmetry group operation rotation by alpha, and using J equals to 8. So I'm going to skip that because this is a simple algebra exercise, and but after you do that, you get for the octahedral crystal field, this is what you get for the equivalence representation. First of all, notice this is a very highly degenerate level, right? 17 states that would be in principle degenerate if we didn't apply either spin orbit or crystal field. So that I actually this is actually I'm already at the manifold in which J equals to 8. So that means that the MJ values, the MJ, so J equals to 8, meaning that MJ goes from -8 to 8. So there are actually 17 values of MJ. This corresponds to this particular this is the dimensionality of this representation, and I can actually decompose that, and after we do that, this gives me a gamma 1 plus 2 gamma 1 2 plus 2 gamma 1 5. This is the O group, right? Plus 2 gamma 2 5. So this is the degeneracies are 1. These are 2 plus 2, 2 doubly degenerate levels, 2 plus 3, and 2 plus 3. So I have 1 non-degenerate level, 2 doubly degenerate levels, and actually 4 threefold degenerate levels. 3 of them are gamma 1 5, 3 of them are gamma 2 5. So this right away gives tells us about the power of group theory in finding the splittings of such a complicated and highly degenerate energy level. Okay. So this is a Homion 3 plus in a cubic environment. So let me do another example. And erbium 3 plus, and also in a cubic field, group O. So for erbium, we have the other possible situation, which is as a half integer J, right? Because erbium 3 plus has a electronic configuration 4f11, 5s2, 5p6, and this corresponds to J equals to 15 halves. All right, this is the spectroscopic notation. So J equals to 15 halves. And again, once you do the calculation of the characters for the equivalence representation, so this is what we get for this case. And just so this is a half integer case, so we are going to see that in this case this level will split in double group representations, and actually this splitting is going to be like that: gamma 6 plus gamma 7 plus 3 gamma 8. This is a doubly degenerate state. This is also doubly degenerate state, and this is actually 3 times 3. 3 times 4-fold the gamma 8 level, giving me a total of 16 levels, which actually corresponds to the possible values of mj. In this case, mj is 15 halves, 13, etc., until minus 15 halves. Gives me a total of 16 levels. And once again, group theory tells me precisely how these levels split. Okay? Alright, this is the different cases I wanted to consider. Let me briefly also say a few words about how we find selection rules for optical transitions in different systems, for instance in semiconductors, using the double groups. It's not very much different from what we did before for ordinary groups. So this is, for instance, a band structure of germanium. And in the double group representation, so you see the valence band has a split in here, this heavy hole, light hole, top of the valence band with gamma 8 plus symmetry, and the split off band, the gamma 7 plus. So we have discussed this band structure in the previous lecture. What we want to try to figure out now is what are the selection rules, for instance, for making transitions from the valence to the conduction band, right? And as I said, it's not very much different from what we have considered before. We have to consider the H prime of light, the perturbation from the electromagnetic field, and as we have seen, this transforms like a vector, right? And in this particular group, the group of the wave vector at the gamma point, this transforms like the gamma 1,5 minus representation. So to see the possible transitions, we have to make direct product. So let's see what are the possible levels that can couple with the bottom of the conduction band, gamma 7 minus, right? So the conduction band minimum, CBM, transforms like the gamma 7 minus representation. So we have to make the direct product of gamma 5 minus and gamma 7 minus, is a double group representation, to see what are the possible levels to couple with the gamma 7 minus level optically, right? And after you do this and decompose, this gives me gamma 7 plus and gamma 8 plus. Remember, again, this is a group in which I have inversion symmetry, so light will couple states with opposite parity. In this case, the top of the valence band, gamma 7 plus and gamma 8 plus are both even under parity, and the bottom of the conduction band is odd under parity. So this is in the literature we refer this band as the heavy hole and light hole bands, because you can notice here there are two slightly different effective mass. One corresponds to an electron with a heavier mass, and not the electron, the hole with a heavier mass, and another one with a smaller mass, a light hole. And this is what we call the split off band, because it splits from the top of the valence band by the spin orbit interaction. But what group theory is telling me here is that actually we can shine light, we can couple both of these two states, the split off state and the heavy hole light hole state, to the top of the to the bottom of the conduction band. So we must expect to have optical transitions from the split off band and also from the top of the valence band, of course with different energies, right? So this is just an example, and so just to show you the way to proceed on how to find selection rules using double group representations. It's not much different from what we have considered before using ordinary groups. Okay, so let's move on and let's see a few examples of basis functions for double group representations. We are using this notation, spin up for spin up and spin down spin states, 1/2 spin states. And as we have seen last time, this form a basis functions for the spinor representation d1/2, which in the case of a cubic group, it corresponds to the gamma 6 plus in cubic symmetry. So this is one basis functions for the gamma 6 plus representation. But the idea now is to see how we combine this spin part of the wave function to the spatial part or orbital part. Spatial component. And we have done this exercise last time, and in which, for instance, when you have a state corresponding to an ordinary group representation gamma 1 plus, and after you add spin orbit interaction, the final symmetry is going to be given by the direct product between that and the spin representation, which in this case is gamma 6 plus. This is one case in which there's no degeneracy breaking by spin orbit. We have also seen an example in which, for instance, you have a gamma 1/5 state, and after you add spin orbit effect, it splits into another gamma 6, but also a gamma 8 plus state. So sometimes it's useful to make a distinction between gamma 6 states arising from different electronic states with different symmetry. For instance, here I have a gamma 6 plus that actually came from a gamma 1/5 plus without spin. And here I have also a gamma 6 plus coming from a gamma 1 plus. So the first thing I want to say is to introduce this notation that the book uses to distinguish between these two gamma 6 plus representations, and the notation the group uses is actually gamma 6 plus arising from gamma 1 plus. That's the meaning of that representation. Or I may have a gamma 6 plus arriving from a gamma 1/5 plus, right? So this is the first distinction that it's important to consider. Oops. Okay. So, having that in mind, let me now see a few examples of basis functions in which I consider both the spatial and the spin part. Okay. And the example I want to analyze initially is the following. Let's suppose I have a gamma 1/5 minus ordinary representations, and after I introduce spin orbit coupling, Then I make the direct product with the spinor representation, and that splits into a gamma 6 minus and a gamma 8 minus. So this is an interesting example to consider, because if you remember, the gamma the gamma 15 minus, the basis for the gamma 15 minus is the vector, right? For the spatial part. And not only the vector x, y, z components, but another possibility is consider p orbitals, px, py, and pz. So these gamma 15 minus states, the orbital character of them can be actually associated to px, py, pz, p orbitals that correspond to angular momentum, orbital angular momentum L equals to 1. Okay? So, and also we know that gamma 6 plus, it's a basis, is a representation sorry, corresponding to spin 1/2 state. So this is the typical example, and we have seen that before in the previous lecture, in which I combine orbital angular momentum L equals to 1 and spin angular momentum S equals to 1/2, and that gives me using the rules for addition of angular momentum, that gives me J, two different possible values of J, L plus F, that's 3/2, and L minus S, that's equal to 1/2. Okay? So from the simple exercise that we did last time, we already know actually how this at two levels, gamma 6 minus and gamma 8 minus, what are their J values, right? We know that this corresponds to a J equals to 1/2, and this will correspond to a J equals to 3/2, because this is what how the spin orbit coupling Hamiltonian will split those states. So the gamma 6 level. So for J equals to 3/2, we have four different possible values of Mj. Mj equals to plus 3/2, plus 1/2, minus 1/2, minus 3/2. So fourfold degenerate state, gamma 8 minus, and for J equals to 1/2, I have only two different values of Mj, plus 1/2 and minus 1/2, and that will correspond to the gamma 6 minus irreducible representation of the double group. So what this exercise here, the objective of this exercise is to see how this 6 different states that I start with, how they arrange themselves, their basis functions arrange in basis functions with these particular types of symmetry, right? So the 6 states that I have initially, as I said, they correspond to px, py, pz, and spin up, spin down, right? So initially I have states px spin up, py spin up, and pz spin up. Also px spin down, py spin down, and pz spin down. So before spin orbit coupling, these would be 6 states would be degenerate, and the degenerate is split in 4 plus 2 when I apply spin orbit. And what I want to do now is to find what are the corresponding basis functions. Okay, very good. So what's helpful in this case actually is that this problem has been already solved when we actually in quantum mechanics study the addition of angular momentum and Clebsch-Gordon coefficients. So that's precisely what the Clebsch-Gordon coefficients tell me, how to go from one description in which I have LML SMS quantum number to the description in which I have J and MJ quantum numbers. So let me quickly remind you what are the Clebsch-Gordon coefficients for this particular case and what they mean. So again, I want to write a certain JMJ state as a linear combination of ML MS states. Okay, and so in this case I have L equals to 1. So I have ML is equal to 1, 0, minus 1, and S equals to 1/2. So I have MS equals to, I can use this plus spin up, spin down, or I could also use 1/2 or minus 1/2, doesn't matter. Okay? So, and these are tabulated Clebsch-Gordon coefficients. You look at Clebsch-Gordon tables and you will see that the 3/2 JMJ state is actually ML equals to 1, spin up. The 3/2 1/2 So let me do first the J equals to 3/2 case, okay? Then we do the, after that we do the J equals to 1/2. So this is square root of 1/3, 1 spin down, plus square root of 2/3, ML equals to 0, and spin up. Okay, J equals to 3/2, MJ equals to minus 1/2. According to the Clebsch-Gordon table, is square root of 1/3 minus ML equals to minus 1. Spin up plus square root of 2/3 ML equals to 0, spin down. And finally 3/2 minus 3/2, it's the ML equals to minus 1, spin down. Okay, so all right, so how can I now make a correspondence between that and the px, py, pz basis functions that I had before for the spatial part? So there is actually a correspondence between the spherical harmonics and the p orbitals in Cartesian coordinates. So I want to make a correspondence between the spherical harmonic YLM and pi equals to x, y, or z. So this is also already, this is well known. We know that the y10 spherical harmonic is actually square root of 3 over 4 pi times z over r. This is what in Cartesian coordinates this is, and this is what we call a PZ state, PZ orbital, right? For the px and the py, it's slightly more complicated. The px is similar to pz. We just substitute x for z, so it's proportional to x over r, and the py orbital is root 3 over 4 pi y over r. Okay. So, but how do I write those in terms of spherical harmonics? So this is actually well known. I can write this, copy that from a book. Py is actually proportional to the sum of angular spherical harmonic 1 minus 1 plus spherical harmonic 1 1, and px is oops, there is not, okay, I wrote square root twice here. This is 1 over root of 1 over 2. I was making the same mistake again. And the sum, or actually now this difference between y1 minus 1 and y1 1. Okay? So if I can now invert this and actually write the spherical harmonic y (1, L equals to 1, ML equals to 1) as root 2 over 2 of px plus I py, and y1 minus 1 as root 2 over 2 of px minus IPY. Okay, great, because after we do that, then since what I have here are precisely this spherical harmonics, different values of ML, I can just go ahead and write, let me try to find some space here. So let me try to find some space here. Let me write here the basis functions for j equals to 3/2, and in terms of px and py and pz, this is going to be 3/2, 1 of root 2, 1 over root 2, and then okay, now I take ML equals to 1 corresponding to this spherical harmonic, and I just substitute that for px plus IPY. So the spatial part is going to be px plus IPY, and the spin part is spin up. Similarly, for the 3/2, 1/2 state is actually going to be 1 over root 6 px plus IPY spin down plus square root of 2/3 pz spin up. the 3/2 minus 1/2 is 1 over square root of 6 px minus ipy, which is ml equals to minus 1, spin up, plus 2/3 of pz spin down. And finally, this state is 1 over square root of 2 px minus ipy spin down. Okay? Alright, so as you see, this is not a very simple exercise, and perhaps you wonder if this is very specific to this particular case, but luckily people have already done this for most of, or maybe all groups, and there are tables for these decompositions. So these actually, we're going to see that in a minute, but this is our final answer for the basis functions, spatial and spin part of the gamma 8 minus state arising from a gamma 1/5 minus, right? And of course one can do the same for the j equals to 1/2. I'm going to skip that because I hope you can see where this is going to, right? But this is tabulated in our textbook. So this is one particular case, and as I said, more general cases you can find all these decompositions in tables. For instance, let's see a few more examples. If you make a correspondence, if you look at you can make a correspondence that we did here for the basis x, y, z, right? You can make a correspondence between x, y, z and the angular momentum components Lx, Ly, and Lz, and this is a basis for gamma 1/5 plus instead of gamma 1/5 minus. So using that, you basically substitute px, py, pz for the operators Lx, Ly, Lz. You get a basis for gamma 8 plus arising from gamma 1/5 plus, just as we did in the previous slide. And also for, if you take j equals to 1/2, you can get basis functions for gamma 6 plus arising from gamma 1/5 plus. You can also make another correspondence x, y, z to the products y, z, zx, and xy, and these are the basis functions for gamma 2/5 plus. So straight away, using the results we have obtained in the previous slide, you can get gamma 8 plus representations are arising from gamma 2/5 plus and gamma 6 plus, 6 plus arising from gamma 2/5 plus, right? And etc. You can use that result in many different flavors, many different possibilities. Okay? So in more general case, then you have to resort to tables. So some of those tables are in the appendix D of our textbook, but you can find all of these tables in the reference material, Miller and Love books, or even online. So this is information that it's already tabulated. So I'm just going to go through a few of these tables just to show you how they look like, right? So how to use the double group tables in Appendix D. So this is one example of that, and this is table D.4, which actually is precisely the case we have considered before. So it gives me the coupling between gamma 1,5 minus and the spinner, which gives me gamma 8, gamma 6 plus gamma 8, and that's this notation. So this is 6 and this is 8, corresponding to the irreducible representations gamma 6 and gamma 8. So the label here is the MJ value, so 3/2, 1/2 minus 1/2 minus 3/2, and these are the different lines, different rows, and the different columns correspond to precisely px spin down, px spin up, py spin down, py spin up, etc. Right? This ux4, what this 4 means is actually the label. Unfortunately, there are many different ways to label irreducible representations for historical reasons, but gamma 1,5 actually can be also known as gamma 4. And that's the reason for that upper label 4. Okay, so that corresponds to gamma 4. So this is actually gamma 4 minus combined with gamma 6 plus. So if you see these numbers, they are precisely, I think, up to a factor of I, a convention, but they are precisely the Clebsch-Gordon coefficients that we have discussed in the previous slide. So this is these tables of double groups, they correspond sometimes to Clebsch-Gordon coefficients. Okay. Alright, so there are several of those tables in Appendix D that may be useful to you. And let's now move on and let's discuss about the combination of plane wave basis functions and double groups. We have discussed the plane wave description of electronic states. I think this was chapter 12, maybe? Yes, so this was chapter 12. We have discussed, for instance, the empty lattice approximation, and this is what you see here in this picture. This is the empty level band structure for a cubic crystal, and as we saw, we could without using without spin orbit, we could see that some of the very highly degenerate levels would split just because of crystal field, just because of the cubic symmetry, right? For instance, this level here, the second lowest energy level at the gamma point, arising from 6 different parabolas, would be a 6-fold degenerate level. This would split into gamma 1 plus, gamma 1 2 plus, gamma 1 5 minus, meaning a 3-fold degenerate plus a 2-fold plus a 1-fold degenerate level. Okay? So what we want to see now is how double groups change or that picture, and also how can we find the basis functions for double group representations and plane waves, using plane waves. Okay. All right, so there are different cases to consider. For instance, in some cases, let's see how the gamma 1 plus level looks like when we introduce spin. So you see that the gamma 1 plus, but also the gamma 1 minus, when you make the direct product between that and the gamma 6 plus, the spinner, gamma 6 plus, you get gamma 6 either plus or minus. So this level is not split by spin orbit. So if you have a gamma 1 plus here, it will basically change the label, change the notation from gamma 1 plus to gamma 6 plus, right? The same happens for gamma 2 plus or minus. When you make the direct product between that and the spinner, you get gamma 7 plus or minus. Again, it's not split. What about the basis functions? So again, the basis functions, it's going to be just the original plane wave basis functions multiplied either by spin up or spin down state. Okay, for instance, a gamma 6 plus or minus symmetrized wave function, let me write that as using that notation, a combination of plane waves, right? So in this case, this would be a combination of all these 6 plane waves here. For the way to write that for a gamma 6 representations is that we start from the gamma 1 combination of plane waves and just multiply by the spin function that could be either spin up alpha or spin down beta. Okay, and the same for the gamma 7. You just multiply the spatial or orbital part, in this case gamma 2 plus or minus, combination of different plane waves, symmetrized. You just multiply by the spin function, the corresponding spin function. So these are, as we have discussed, symmetrized plane wave combinations, right? So what about slightly more complicated cases? So let's take now gamma 1 2. Gamma 1 2, even or odd, when you apply spin orbit coupling, it goes to it does not split. It becomes a fourfold degenerate level, right? Gamma 3 plus or minus. Oh, sorry. This is the same state, but using a different notation, right? And so this is actually, you can see that here in this table. The original, this results from the direct product between my original gamma 1 2 and gamma 6. It's what we call in double group gamma 3. And that gamma 3 is it's actually the same as the gamma 1 2 that I had before. So you see, these are the basis functions for gamma 3. Okay, and how do we find then the symmetrized combinations of plane waves and spin. We have to look at those tables. So this is a table D5, and once again you see that this is how, for instance, so I think I made a mistake here. So the gamma 3, when I make the direct product, so gamma 3 is actually the same as gamma 1, 2, and when I make a direct product between gamma 3 and gamma 6, I get a gamma 8, fourfold degenerate level. Okay, so how is the combination, the proper linear combination of plane waves that I should use? So this table precisely gives me that combination. So these are the gamma 8 states, and this is how they relate to the product of spin and spatial part. So U1 and U2 here basically are precisely these two basis functions of the gamma 3 representations. This is U1 and this is U2. Okay, so using this table I can get all the 4 different states of gamma 8 plus or minus, and these are the different combinations of spatial and spin part. And if I want to transform that in plane waves, I can just make that familiar correspondence between x square, y square, z square, with sines and cosines of plane waves. Okay, that we have done that in exercises. So using that correspondence, I can write any linear combinations of plane waves that I want to. All right, so this is the way to proceed. And also, let me do another one for threefold degenerate level. That's the same idea. Let me go back to this case in which I have this is, for instance, gamma 1,5, either plus or minus. Oh, okay, I wrote that here. If I have gamma 1,5 combined with the spinor representation, that splits into a gamma 6 and a gamma 8. If I have gamma 2,5, splits into a gamma 7 and a gamma 8. And I can use the same idea. I can use this different tables and write these different combinations. Okay, this is a gamma 6 plus, this is a gamma 7 plus, and basically what I do is that I use as ux, uy, uz the tabulated basis functions that can be different depending if I start from a gamma 1,5 or from a gamma 2,5. So there's a correspondence between these tables and the character table and tabulated basis functions. Okay, and I hope you can see what the idea is. All right. Finally, let me end with a discussion of the effects of double groups and spin orbit coupling in non-symmetric groups, and specifically on the bands that stick together in some high symmetry points of the Brillouin zone because of glide planes and screw axis operations, non-symmetric groups. We have seen this before without for ordinary group representations. We have seen that in some cases the structure factor of the crystal potential vanishes, and that means that bands are degenerate. Because of that, bands are degenerate at some specific points in the Brillouin zone. We saw, for instance, the case of the X point for the diamond structure, and we also saw the case of the A point for a HCP structure. Okay, now we are going to discuss another possible case, which is the A point in graphite. So this is the crystal structure of graphite, as it has is a stacking of graphene planes, but they are arranged in AB stacking, meaning that this is the full unit cell, and each unit cell has actually two planes, and there is non-symmetric operations that actually need a translation by C/2, right? So there are non-symmetric operations that require a translation of a partial vector within the unit cell C/2z. Okay, so this is a non-symmetric group, and because of that, bands will stick together at the A point in the Brillouin zone. Okay, the A point is precisely that, I mean, corresponding to the wave vector associated to this translation. In other words, A is actually pi over c z. This is the A point here in the Brillouin zone, and you can see that at the A point, bands stick together. There are degeneracies here precisely because of that. Okay, now, so the idea here is to see how spin orbit coupling may or may not change that, and that's is not very different from what we have considered before. We have to look at the character tables for the group of the wave vector at the A point. So this is the character table for the group of the wave vector. The double group character table, right, for the group of the wave vector at the A point, and it may also be useful to look at the compatibility relations between A and the delta line. So the delta line is actually the line between gamma and A, right? So if we look along this direction, and specifically in this particular picture, what I see here is two delta lines. So this is the A point in the Brillouin zone, and I can go to gamma along this way and in this direction. So this is a gamma A gamma band dispersion, okay? And these are delta lines. So again, you find all the different irreducible representations for the double group at the A point. They are labeled A1, A2, A3, A4, A5, A6, and you can do in the usual manner the compatibility relation between the A point and the delta line. And after you do that, you see that A1 splits into delta 1 plus delta 3, A2 splits into delta 2 plus delta 4, and so on and so forth. Okay, so this is what I mean by these drawings, these pictures here. So the A1 level is degenerate because of these non-symmetric operations, and they split, and when you move away from A, they split into a delta 1 and a delta 4, and the bands are linear here. Okay, very similar to the case of diamond that we have considered before. But there is one interesting case here, which is the A4 and A5 representation. We may see that in the next few lectures or seminars when we consider time reversal symmetry. Because if we look at the A4 and A5 irreducible representations, you see that the characters are the complex conjugate of each other. And when that happens, this is a signal to us that these two states, they are actually degenerate because of time reversal, which is it's not a spatial symmetry, but time reversal symmetry, which we have not considered so far. We're going to see that in a few days, right? So, and that's the meaning of this picture here. So here, I actually have a fourfold degenerate level, because both the A4 and the A5, they would be both twofold degenerate each. They are also degenerate because of time reversal, okay? And so this is a fourfold degenerate state. And we will perhaps see that in the next few lectures, okay? All right, so this is it for today, and thank you for your attention.